Okay guys, so annoyingly enough, the previous software I was using discovered that it just had a bunch of issues. So now I have to jury rig a thing where I edit together a voice recorder, which is a default application on Windows, and use Shadowplay to record my desktop now. So we'll just see how that works. So yeah, let's go from there. So because of all that messing around, I don't actually have anything open right now, so just bear with me for a minute. Alright, so where we dropped off is that we'd added the plus equals 2 to the columns. So now let's begin counting our neighborhoods. We'll use a very simple function that returns an integer called countNeighborhood. And it'll take our rows, our columns, and our... Oh, I'm sorry. I copied and pasted the wrong thing. There we go. So count neighborhood, chart matrix, and I'll just name this simulation for consistency. So it'll take our rows, our columns, an x-coordinate, and a y-coordinate of the home cell. If you watch the prequel, you understand what that means. And it takes the simulation. So, I'm just going to copy and paste this definition down here. And we'll need it before step simulation, actually. But for now, we haven't created step simulation, so I'll just do this. Because in order for step simulation to work, we actually need to be able to count the neighborhood first. So there's some easy ways to do this, and there's a fancy way to do this. I opted for the fancy way because it actually ended up being easier and quicker, since I only had 2 hours to write the game of life, because I did not know that it was due on that day. So basically, we create a counter variable, and it'll initialize that to 0. We take something called the pivot, and this will look familiar. This is mostly just to make things easier to see, but basically the pivot, you've seen it here already. So just bear with me for a minute. For int I equals -1, I is less than or equal to 1, I plus plus, and we'll do the same for a variable named j. And then we will assign the cell to a variable called c, and then we'll do simulation plus pivot plus I times columns plus j. So the long and short of it is the simulation. We're accessing it like normal here, but now we need to look around the neighborhood. Well, actually I wish I hadn't deleted the neighborhood that I had right there. So just give me a minute to recreate the neighborhood. Alright, now we've got our neighborhood. It's filled with just numbers. They don't mean anything in particular. So let's say our home cell is here. So how we access the home cell is we multiply y, which is, remember, y is equal to height and regular Cartesian coordinates. So y, let's say that y is 1. So we're going to want to be 1 row down. So we multiply that by the number of columns, because it's not actually, when you access memory, it doesn't actually look like this. It's all in a straight line like this. So we have to do some fancy tricks to treat it like this. So y times columns brings us down here, plus x, which is our index. So this would be 1, 2, no, 3, or 4. So it'd actually be 2, 4, since I didn't account for the special rows. So now that we're here, what happens if we add a negative I times the columns? Well, that's going to bring us up here. Okay, that's all well and good, but now what happens if we add j? Well, that adds a negative 1 to x. Our x was 4, plus a negative 1 now brings us here. So it brings us to our top left. And it basically just repeats that whole process as it goes to here, to here, to here, to here, to here, to here, and to here. So this is basically what it would look like if we did it like that. We could do that for all of them, if that helps, but I wouldn't recommend it. So basically, it adds a negative column, which is here. It adds a negative column, which brings us up. It then iterates through the entire top row, starting with the top left, because it adds negative 1, adds 0, remember, because minus row brings us up here. And since we don't add anything, it just brings us right up there. Then we add 1. Then we repeat the process by 0 times columns, which means nothing. So we stay here. Then, since j is minus 1 and we add that to x, that brings us over here. Then plus 0, that brings it to us. And then here. And then it repeats the process for a 1 times column, so it brings us down here. Minus 1 brings us over here. So that's how it works. And I hope that's not too terribly confusing. I can explain it better in the comments if you still have an issue. So this is what we'll do it. Now, what does it mean when a cell is alive? Well, that means it's the pound character. So if c is equal to the pound character, count plus plus. So, we don't want to count ourselves, so what we can do right here is if I is equal to 0 and j is equal to 0, count minus minus. Actually, no. I'll go over that in a minute. But we won't want to count ourselves. I'll just show you. Since we won't actually do it within the count neighborhood, we'll do it after we get that data. And that's the gist of the counting the neighborhood. We just return our count, and that's how we do things. So, now that we've done that, we can actually create our step simulation function, which looks like this. It works a lot like the create function, except it's going to take the previous simulation as an argument, but it's also going to return a new simulation. And we're just going to name it step for the purposes of this video. Int rows, int columns, and then prev matrix, or sorry, prev simulation. So now that we've got our step function defined, our prototyped, we are now going to define it. I'm going to define it all the way at the bottom. Or rather, it's actually going to need to be above the begin function, since that's how things work in C, unless you've got header files. But you won't actually need header files for the console version of this project. And I'll go over there. We'll go over header files once we start working in GUI. So now we've got our step function. This is when you need to bring up the rules, which were... I appear to have moved it, so I can't actually get to them. But if we were to Google Game of Life rules, there we go. And we just go down here, we'll see these 3 things. And I'm just going to copy those into the comments, so that we know what we're working for. Oops. Okay. So, what is one of the things we're going to have to do if we're going to iterate through the entire neighborhood? Or not neighborhood, the entire simulation. Well, we're getting ahead of ourselves there. First, what we need to do is we need to create a new simulation, or rather, a new thing to hold our simulation. So we're going to call it stepped simulation, and we're going to equal to calc rows times columns So this is going to function basically the same way as creating a simulation, except we're not going to seed it this time. And of course, one of the best practices is to check if it is null. Since we won't be able to do anything anyway, it would just cause a crash. And we're going to iterate over it the same way that we've iterated over everything else. The explanation as to why is in the previous video. Whew, man, I've been typing that a lot. Alright. Oops. So now that we can iterate over our entire simulation, what we're going to want to do is we're going to want to count the neighborhood of each individual cell. Well, we'll just name it a handy-dandy variable called live, and we're going to call count neighborhood, the function we just created. Rows, columns, x, y, prev simulation. And remember, the previous simulation is actually our current simulation. This is our future generation. So now that we've got live, we're going to first check the cell for what type it is, if it's alive or not. Times columns plus x. If cell is equal to, if it's alive, then we're just going to decrement our count. Since we don't want to include ourselves, since we're not technically considered to be in our own neighborhood, since the neighborhood is the surrounding cells and not the home cell. Okay, now that we've got that over with, we look at these rules. So any cell with fewer than 2 live neighbors dies. Alright, that's simple enough. So if live is less than 2, then we say, now don't do prev simulation, we are now putting things inside the stepped simulation. And we're going to say it is now dead. Okay, what's our next rule? If, any live cell with 2 or 3 live neighbors lives on to the next generation. Simple enough. If live is equal to 2, or live is equal to 3, and we're going to want to put this in parentheses. I'm pretty sure that wouldn't cause an issue, but I like to make sure that this will absolutely work. But we need to make sure that our cell is alive. And we're just going to move in a live cell. Plus y times columns plus x. I'm going to be typing that a lot actually, so I'm just going to copy and paste that. Since it's going to stay alive, so we're not going to do much. If any live cell with more than 3 neighbors dies, as if by overpopulation, simple enough. We can actually just copy and paste this, and then say if live is greater than 3, and the cell is alive, then we're going to kill the cell. Oops, I meant to be putting else's here, though I'm sure it wouldn't cause a problem. I just like to make sure that my program is structured as it should be. But now we're looking at a dead cell. So again, we could just copy and paste this. If life is exactly 3, and the cell is dead, we're going to make that cell come alive. And those are the rules of our simulation. Alright, and now we can free our previous matrix. Although, I probably shouldn't be doing that in this function, since that would result in funky behavior. Not really funky behavior, but it'd just be good practice, so that you don't think that that you haven't freed memory, that you've already freed. Quick note, freeing memory is like recycling the paper. You don't get to use that paper anymore, but it goes back to the system, or the paper man, however you want to look at it. And then we're going to return our stepped simulation. So I think this might actually be the end of the video soon, assuming that everything works correctly. So now that we've gone through all of that, we can actually do this. So now we're going to go back to our begin function, and we're going to do something that's very highly, it's not recommended at all, but we'll do it since it's a console program, for crying out loud. So then, while 1, this is a permanent loop. You cannot get out of this loop. So it's going to loop forever. Until you press Control-C, which quits the program. Alright, int temp sim, or not int, jeez, I keep thinking about my GUI version. Sim is equal to create, or no, sorry, step. There we go. Rows, columns, and our previous simulation. And we're just going to name this new sim. Then we're going to give the paper back to the paperman, simulation, and then we're going to set simulation equal to new sim. But first, we of course need to check if new sim is null. And we're just going to return, which means quitting out of this, since we couldn't get the memory, so we're not going to try again. Simulation is equal to new sim, display, rows, columns, rows, columns, and our simulation, of course. Then, since we're on Windows, or actually, oh shoot, this might actually be a problem. So we need to find a way to sleep the program, but since I'm using Bash, that actually changes things for me. I have to use Linux's version of sleep rather than Windows's version. So I don't actually know what to do here now. I don't want to confuse you guys by using the Linux version, but at the same time I don't want to alienate the Windows users. Okay, so this is Windows specific. So if you're on Windows, follow these instructions. You're going to include windows.h, then you're going to go down here, and you're going to say sleep for 1000. I'm pretty sure that's not a capital, actually it is a capital S. So a capital S sleep, because Windows is funky like that. So this is sleeping for 1000 milliseconds, which is 1 second. For the, and if that doesn't compile, it might be a lowercase s. For Linux, you need to include a special library as well called UniStd. So Unix standard. Unix is the predecessor to Linux. So Unistandard means Unix standard. And you'll use this only if you're using Linux. Now, Linux takes sleep a step further. they do it in microseconds. So 1 second, or sorry, is 1 million microseconds. So instead of 1,000, we're going to do 1 million. So that's 1,000, 10,000, 100,000, 1 million. There we go. So that is going to tell it to pause for 1 second between each simulation. If everything has gone correctly, this should compile and work just fine. So let's try it out. I've got my fingers crossed. Implicit declaration of you sleep? That's actually very strange. I included the correct library. It's supposed to be you sleep. I don't quite understand why it's causing a fuss. Well, whatever. It allows implicit declarations anyway. So 10 by 20. And you'll notice that it looks like some funky stuff is actually happening. So we got a correct still life, but we also got some weird still life. And the problem is that we're not doing something strange. Oh, that's right. If something doesn't happen to a cell, then sometimes it won't get copied over correctly. So what we do is we do something that's a little wrong, but you know what? I'm going to do it anyway. Well, it's not wrong. I don't actually know if it's considered bad practice. So we're going to do step simulation plus y times columns plus x is equal to cell. So that should fix all of our problems. This will copy over every single cell, and if one of the rules applies to it, it'll just change that cell. But this makes sure that everything gets copied over, regardless. So let's try that again. And would you look at that, everything's working fine. You'll notice several patterns have started to emerge. For one, there was a still life there a minute ago. You notice this one died out, this one's also going to die out, and this one's going to explode. So, one of the things about Conway's Game of Life is you can never tell when it's going to end. It's actually mathematically impossible with our current level of mathematics. Even in like the PhD realm, it's impossible. So you'll notice that now we've got a form of active life, and we got a form of still life, and we'll see what this appears to be. So this is one of the things that happens with our borders. Since there's no wraparound allowed, you'll sometimes get strange patterns that wouldn't exist on a real grid. So you'll get stuff like this. But in the next video, we will actually go over applying the borders, meaning copying the cells from here into the invisible border, etc. So that's all I have for you today. So I hope that all of this was well explained, and I hope that everything goes well. So thank you for watching, and have a wonderful day.